Hello dear students, myself Mohammad Wasim, Assistant Professor in Mathematics, Art Science, Commerce College, Bangladesh. As we know that we have studying about integral transform, in which we have completed our two chapters. One is Laplace transform and another is inverse Laplace transform. Today we will see the application of Laplace transform and inverse Laplace transform in differential equation. So today we will start our new chapter, chapter number 4, application to differential equation. Application to differential equation. Now, in advanced research, we always or frequently come across a complex differential equation which is not easily solvable. So, we apply Laplace transform to that differential equation and convert that differential equation into algebraic form. And we know many methods to solve algebraic equation. We solve that algebraic equation and convert that algebraic equation into Laplace solution by using inverse Laplace transform. So consider we have one equation. Consider we have an equation that is a y double dash b y dash plus c is equals to c y d or f of t, where t y is independent variable, y is dependent variable and t is independent variable. Now, if it is very complex differential equation and we are not able to solve such type of complex differential equation directly, then we use Laplace transform to convert this complex differential equation into algebraic equation, and we know many methods to solve algebraic equation. After solving that algebraic equation, we convert that algebraic solution by using inverse Laplace transform in the solution of the Laplace equation given by Laplace equation given in the question. So we directly apply Laplace transform to such type of equation. Apply Laplace transform to the above equation. That is equation star. Now, applying Laplace transform to this our equation, we will get a y double dash plus b y dash y equals to Laplace transform of f of t. Correct. Now, since we know that Laplace transform satisfies linearity property over addition and subtraction, so the operator Laplace transform can be distributed over a y double dash plus Laplace transform of b y dash plus Laplace transform of y. So we will distribute a y double dash plus Laplace transform of b y dash plus Laplace transform of y and Laplace transform of f of t. Correct. Now, since a is constant here, b is constant here, so we can take it outside of the Laplace transform So we will get A Laplace transform of y double dash, B Laplace transform of y dash, and Laplace transform of y as it is, and Laplace transform of f of t. Now we have applied Laplace transform to equation star, and we have distributed the operator over each term of that equation. Now we have to use Laplace transform of differential equation or differentiable function, or we have used Laplace transform of derivative at this point. Now applying Laplace transform of derivative, Laplace transform of derivative, and we know that we have Laplace transform of y raised to n is equals to s raised to n Laplace transform of y, then minus s raised to n minus 1 y of 0, then s raised to n minus 2 y dash of 0, and s raised to n minus 3 y double dash of 0. Similarly, in this way we will get y n minus 1 of 0. We know that we have studied about Laplace transform of derivative in the first chapter, Laplace transform, and we have the formula if we want to find Laplace transform of function which has nth derivative, then we can write it as in the form of s raised to n into Laplace transform of y minus s raised to n minus 1 y of 0. Similarly, s minus s raised to n minus 2 y dash of 0, and in this manner up to minus y raised to n minus 1. Correct? And we can write it as s raised to n y of s. Since we are taking Laplace transform of y of t, we will get y of s, and s raised to n minus 1 y of 0, s raised to n minus 2 y dash of 0, and minus y raised to n minus 1 of 0. Now putting this value in this equation A, since we have only Laplace transform of y double dash, so since here we have double dash means second derivative, we start with s square Laplace transform of yt, then reducing power of s, you will get 2 minus 1, that is 1, y of 0, then again reduced by 1, you will get s raised to 0 y dash of 0. Correct? And we can write it as s square y of s minus s y of 0 minus y dash of 0. See, s raised to 0 becomes 1. So we have Laplace transform of y double dash is equals to s square y of s minus s y of 0 minus y dash of 0. Similarly, we can find Laplace transform of y dash, and since we have only first derivative, so we start with s and power is 1. Since number of derivative is equals to power of s, in this formula we can use s raised to 1 Laplace transform of y t minus s minus 1 minus 1, that is 0, and y of 0. Correct? So we will get s transform of yt is equals to ys, where y represent capital Y, and whenever we use y dash, y double dash, it is in small letter, and it is value which is given in the question by using initial value problem or boundary value problem. So by using these value in this equation, we will get a is equals to, now Laplace transform of y double dash, which is equals to s square y of s minus s y of 0 and y dash of 0. Correct. Now plus b as it is, plus b as it is, and Laplace transform of y dash, which is equals to s y of s minus y of 0, and Laplace transform of y, which is equals to y of s, and Laplace transform of f of t will give us capital F of s. Correct. Now by applying a into this bracket, b into this bracket, we will get a s square plus b s plus 1, taking y as outside. It has 1 as a coefficient. We have take y of s common outside, and we have a s square plus b of ds plus 1 y of s. Similarly, minus as minus b y of 0 and minus a y dash of 0. Y dash of 0 is equal to f of s. Now putting the values of y of 0, y dash of 0 into this equation, we can find the value of ys, which is solution for this equation. After taking inverse Laplace transform of that solution, we will get the exact solution of particular differential equation. So this is the theory part of this chapter. We will start or go through some examples which are very easy to understand. The equation is, our example is as follows. Solve by using Laplace transform the differential equation. Solve the differential equation, DE, differential equation, by using Laplace transform. An equation is given as y double dash plus 9y is equals to cos 2t with boundary condition y of 0 is equals to 1 and y of pi by 2 is equals to minus 1. Correct? Now we have to find the solution of this question. Solve the differential equation by using Laplace transform. We have to apply Laplace transform to this differential equation, and Using these boundary conditions, we have to find the solution of this equation. So, apply Laplace transform to the following two the whole equation. We will get Laplace transform of y double dash small y double dash 9y and Laplace transform of cos 2. Now since Laplace transform satisfies linearity property, so we can distribute the operator over both expression. Now since here we have y double dash, so we can write it as s square Laplace transform of y. Now reduced by 1 as y of 0 minus reduced by 1 s raised to 0. There is no need to write s y dash of 0. Correct. Now plus Laplace transform of y and Laplace transform of cos 2t will give us s upon s square plus 4, since cos at Laplace transform of cos at is equals to s upon s square plus a square. Correct. Now applying Laplace transform to y, we will get s square y of s minus s y of 0 y dash of 0 plus 9 y of s upon s square plus 4. Now putting values of boundary condition. We have boundary condition y of 0 is equals to 1 and y of pi by 2 is equals to minus 1. So we can write s square ys plus 9y s square plus 9 is equals to ys minus s value of y of 0 is equals to 1. So we can write it as 1. Y dash of 0 is not given, so consider it as a. Consider y dash of 0 is equals to 8 and is equals to s upon s square plus 4. So we have s square plus 9 y of s is equals to a plus s upon s square plus 4. Correct. Now y of s is equals to a upon s square plus 9 s upon s square plus 9 and s upon s square plus 4 into 1 upon s square plus 9. Correct. Now we have to apply inverse Laplace transform to this example. Now applying inverse inverse Laplace transform we will get inverse Laplace transform of y of s is equals to inverse Laplace transform of a upon s square plus 9 plus s upon s square plus 9 plus s upon s square plus 4 and s square plus 9. We will get y of t here inside. Now, inverse Laplace transform of a upon s square plus 9 plus inverse Laplace transform of s upon s square plus 9 plus inverse Laplace transform of s upon s square plus 4 s square plus 9. Now, what we have done, we have applied Laplace transform to this differential equation, and we have given boundary condition as y of 0 is equals to 1, y dash y of pi by 2 is equals to minus 1. Now by applying Laplace transform to y double dash plus 9y is equals to Laplace transform of cos t, we have applied here Laplace transform of derivative. By using the theorem, we convert this Laplace transform of y double dash into s square Laplace transform of y minus s of y 0 minus y dash of 0. By taking y of s constant or y of s common outside from bracket, we will get s square plus 9 y of s minus s y of 0 as given y of 0 is equals to 1, boundary condition. So we can substitute 1 instead of writing y of 0, and y dash of 0 is not given, so we consider y of 0, y dash of 0 is equals to a. Now putting this value and taking inverse Laplace transform of this expression, we will get a. We have 1 upon s square plus 9, that is 1 upon 3 sin 3t. This is formula for cos 3t inverse Laplace transform of s upon s square plus 9, that is cos 3t. And this expression inverse Laplace transform of s upon s square plus 4 and s square plus 9. This is a function which has two functions in multiplication. So we can't directly find the solution of this equation. So by using partial fraction, we can solve this equation s upon s square plus 4 s square plus 9 Now we can write s upon s square plus 4 and s square plus 9 as by using convolution theorem or by partial fraction. We will solve this expression and put value instead of inverse Laplace transform of s upon s square plus 4 into s square plus 9. We will get one upon 5. We will get 1 upon 5 s upon s square plus 4 minus s upon s square plus 9, and inverse Laplace transform of this we will get 1 upon 5 cos 2t minus cos 3t. So we will get a upon 3 sin 3t plus cos 3t plus 1 upon 5 cos 2t minus 1 upon 5 cos 3t. Now by using it is y of t. It is y of t. Now putting y of pi by 2 is equals to minus 1. So we will get minus 1 is equals to a upon 3 sin 3 pi by 2 cos 3 pi by 2 1 upon 5 cos 2 pi by 2 minus 1 upon 5 cos 3 pi by 2. Now putting values of this cos sin 3 pi by 2 cos 3 pi by 2 cos pi and cos 3 pi by 2, we will get a is equals to 12 upon 5. We will get 12 upon 5. A is equals to 12 upon 5. By putting this value, we will get y of t is equals to 12 upon 5 into 3 sin 3t plus cos 3t plus 1 upon 5 cos 2t 1 upon 5 cos 3t. 3 4 upon 3 sin 3t plus cos 3t 1 upon 5 cos 2t minus 1 upon 5 cos 3t. It is a required result for this example. Today it is enough for this day. We will continue with more example in next lecture. Till then, thank you. Bye.